Hello students, in today's lecture we are going to discuss the solution of a differential equation about a singular point. In yesterday lecture we discussed about the ordinary point and singular point. As you can see, this is our previous lecture. We discussed an ordinary point if at a point x equals to a, the differential equation, this differential equation p naught of x doesn't equal to 0, then this x equals to a is called ordinary point. However, if at this point this p naught of x is equal to 0, then that point is called singular point. So in yesterday lecture we solve a differential equation about the ordinary point, and now we are going to solve the differential equation. We are going to find the series solution of differential equation about a singular point. So this is our topic, the solution of differential equation about a singular point. So let me remind you again that what is singular point. If at point, let's suppose x equals to a, if p naught of x is equal to 0, clear? If it is analytic, then this point is called the singular point. X equals to a is a singular point. Of the differential equation. Clear? So singular points are of two types. One is regular singular point and the other is irregular singular point. Singular points are of two types. One kind is regular singular point, and another kind is irregular singular point. So now we are going to know what is singular and the regular singular, and the other is irregular singular point. So first consider the equation. Consider the differential equation. Let's suppose this is y double prime plus p1 of x y prime plus p2 of x y, which is equal to 0. Let this is equation number 1, or we can write it as d square y upon dx square plus p1 of x dy upon dx plus p2 of x y. So by y prime we means y prime is actually d square y upon dx square, and by y prime we means dy upon dx. Clear? So assume that at least one of the function, either p1 or p2 is not analytic. By analytic we mean that if p1 is equal to infinity or p2 is equal to infinity at x equals to a. So that x equals to a is a singular point. Of the given differential equation. Clear? Let we have a differential equation of this kind, and we assume that either p1, this function, or this function p2 is not analytic. This means that either this is not infinity or this is not infinity at a point x equals to a. Then this point is called singular point. So if consider q1 of x, this is x minus a p1 of x, and q2 of x, which is equal to x minus a whole square p2 of x. If q1 and q2 are analytic, this means that by analytic we means this is not infinite at x equals to a, then this x equals to a is called regular singular point. Other, if q1 of x equals to x minus a p1 of x, and q2 of x equals to x minus a whole square p2 of x, and either at x equals to a, if we substitute x equals to a, either q1 or q2 they are analytic. This means that it doesn't go to infinity, then such a point is known as regular singular point. And if other value, then other is called irregular singular point. Clear? So now I hope you understand the definition for regular and irregular singular point. So let's solve an example over the regular and irregular singular point. Example: find the regular singular point. Regular singular point of the differential equation, which is 2x square d square y upon dx square plus 3x dy upon dx plus x square minus 4y, this is equal to 0. So we are asked to find the regular singular point of this differential equation. So solution: dividing the whole equation by 2x square. So by dividing by 2x square, we will get d square y upon dx square plus 3x divided by 2x square dy upon dx. So here 2x square will be cancelled with 2x square, and here this is 3x divided by 2x square plus x square minus 2 minus 4 divided by 2x square y, which is equal to 0. Here this square will be cancelled with this x, and we will get d square y upon dx square plus 3 divided by 2x into dy upon dx plus x square minus 4 divided by 2 x square into y, which is equal to 0. So now compare this with the given differential equation. Here in the statement we have, this is y double prime, and here instead of p1 of x we have 3 over 2x, and instead of p2 of x we have x square minus 4 over 2x. So there here we have p1 of x and p2 of x. Therefore q1 of x will be equal to x into p1, and this is actually p1. q1 will be equal to x dot 3 divided by 2x, and this will be equal to 3 divided by 2. This is q1. And for q2 we can write it as x square. Here q2 is x square minus x minus a whole square. So this will be x square into p2. This will be x square, and for p2 here we have x square minus 4 divided by 2 x square. Clear? So this x square will be cancelled with this x square, and we will be left with 1 upon 2 into x square minus 4. So here is q1 and this is q2. So by putting x equals to a or x equals to 0, here since we see that from q1 and q2, since both p1 and p2 are not analytic, this means that both p1 and p2 p1 is equal to infinity, p2 is equal to infinity when we put x equals to 0 at x equals to 0. Here this is p1, 3 upon 2x, this is p1. If you substitute x equals to 0, then p1 is infinity. And for the same case, if you put here x equals to 0, this p2 is also infinity. Therefore x equals to 0 at this point. Both p1 and p2 are analytic. Moreover, both q1 and q2 are analytic. This means that q1 doesn't go to infinity, and similarly q2 doesn't go to infinity at x equals to 0. Here we see that if x equals to 0, then p1 goes to infinity, so this is not analytic. p1 and p2 are not analytic. However, q1 and q2, it doesn't goes to infinity. They doesn't go to infinity. p1 is infinite, similarly p2. However, q1 and q2, they doesn't go to infinity at x equals to 0. So this means that they are analytic. So hence x equals to 0 is a regular singular point of the given differential equation. So x equals to 0 is a regular singular point. Of differential equation 1. Clear? So as in another example, let's also find another regular singular point. Another example, find the regular singular point of the differential equation, which is x square into x minus 2 whole square y double prime plus 2 into x minus 2 y prime plus x plus 3 into y. This is equal to 0. So here we are asked to find the regular singular point of this equation. Solution. Let this is equation number 1. So again, dividing the whole equation by x square into x minus 2 whole square, so we will get y double prime plus 2 into x minus 2 y prime divided by x square into x minus 2 whole square plus x plus 3 divided by x square into x minus 2 whole square into y. This is equal to 0. So again, by comparing with this equation, here p1 of x will be, p1 is 2 into x minus 2 divided by x square into x minus 2 square, or this will be equal to 2 divided by x square into x minus 2. Clear? So this is p1, and for p2, and p2 is this term, which is x plus 3 divided by x square into x minus 2 whole square. Since here we see that this p1, when x equals to 0, when x equals to 0, this p1 goes to infinity, and also it goes to infinity at x equals to 2. So similarly, for this p2, if x equals to 0 and x equals to 2, so at these 2 points p1 and p2 both are going to infinity. So these are the at this point p1 and p2 are not analytic. Here p1 and p2 are not analytic. This means that p1 goes to infinity and p2 goes to infinity at x equals to 0 and x equals to 2. So these 2 points are singular points, hence both these points are singular points of x equals to points of equation number 1. Clear? Here you can see from these 2 equations, if you substitute x equals to 0, p1 is goes to infinity, and similarly if you substitute x equals to 2, p1 goes to infinity, and the same case is for p2. So both x equals to 0 and x equals to 2, at these 2 points, these 2 points are the singular points of the given differential equation. Since for checking for x equals to 0 first, at x equals to 0, we are going to find q1. q1 is x dot p1. Clear? So this will be x into p1, which is 2 divided by x square into x minus 2, or this will be equal to 2 divided by x into x minus 2. And q2 will be equal to x square p2. This will be x square p2 is x plus 3 divided by x square into x minus 2 whole square. Clear? So these x square will be cancelled, and we will get x plus 3 divided by x minus 2 whole square. So since now if you substitute x equals to 0, q1 goes to infinity, and similarly for this one, if x equals to 0, it doesn't go to infinity. Since Q1 is not analytic, This means that Q1 goes to infinity at x equals to 0. So x equals to 0 is an irregular singular point. Clear? Here we discussed that if at x equals to at any point Q1 and Q2 are not analytic, it means that Q1 doesn't go to infinity, then that point is called regular singular point. But here we see that Q1 goes to infinity at this point, so it is an irregular singular point. Now for x equals to 2, here we found x equals to 0. Now for x equals to 2, for the second case, x equals to 2. Q1 will be equal to x minus 2 into P1. Clear? So this will be x minus 2. Here this was x minus 0, so this will be x, and here we are going to find at x equals to 2, so this is x minus 2 into P1, and P1 is 2 divided by x square into x minus 2. So here this x minus 2 is cancelled with this x minus 2, and Q1 will be, Q1 is equal to 2 divided by x square. And now for Q2 is equal to x minus 2 square into P2. So this will be equal to x minus 2 square into P2 is x plus 3 divided by x square into x minus 2 square. So this x minus 2 whole square cancels with each other, therefore this Q2 is equal to x plus 3 divided by x square. Clear? So now at x equals to 2, when x is substituted here 2, so this will be 2 upon 4, which is equal to 1 over 2. And for this case, if you substitute x equals to 2, so this will be 5 upon 4. So in both the cases, since both Q1 and Q2 are analytic, this means that Q1 doesn't go to infinity and Q2 doesn't go to infinity at x equals to 2. So x equals to 2 is a regular singular point. So for the given differential equation, we find that it has two singular points. One is x equals to 0 and the other is x equals to 2. But at x equals to 0, this is irregular singular point because at this point q1 is not analytic, while at x equals to 2 both q1 and q2 are analytic. So this is a regular singular point. The solution of a differential equation about a regular singular point can be obtained, and the cases of irregular singular points here, that is beyond the scope of our course. So we are going to only find the solution of differential equations about the regular singular points. So in the next lecture we are going to find the procedure or the method for the solution of differential equations for a regular singularity. Thank you very much.